This is the second of 3 videos in Module 1, and in Module 1, Section 2, we will discuss many things about fractions, how to simplify fractions, how to rewrite fractions in a different form, how to add, subtract, multiply, and divide fractions. And so let's get started with a few terms. A fraction is a quotient of 2 numbers. Remember, quotient from the last video means a division problem. So a fraction is nothing more than a division problem rewritten in a different way. The numerator is the top number, the denominator is the bottom number. When we speak about simplifying fractions, which we will speak about a lot, that involves factoring the numerator and denominator into prime numbers. And when we do so, we can apply the fundamental principle of fractions. And the fundamental principle of fractions says that we can cancel common factors in the numerator and denominator. So let's try a few examples of simplifying fractions. The first step to simplify any fraction is to write the prime factorization for the numerator and for the denominator. I'm going to start doing that by making factor trees. So let's make a factor tree for 30. To do so, hopefully you remember we divide 30 by prime numbers until we have all prime numbers at the ends of each of our branches. So I start with 2. 30 divided by 2 is 15. 15 we can divide by 3, and that is 5. 2, 3, and 5 are prime, so the prime factorization of 30 is 2 times 3 times 5. Let's do the same thing with 48. 48 divided by 2 is 24. 24 divided by 2 is 12. 12 divided by 2 is 6. And 6 divided by 2 is 3. We have all prime numbers, so the prime factorization of 48 is 2 times 2 times 2 times 2 times 3. Once we have found the prime factorization for both numerator and denominator, we're going to replace the original numbers with the factorizations. So 30 equals 2 times 3 times 5. 48 equals 2 times 2 times 2 times 2 times 3. And using the fundamental principle of fractions, we can cancel the 2's that they have in common on top and bottom, and the 3's we have in common on top and bottom. Now that does not cancel out every factor in the numerator and denominator. So with whatever factors we have left, we multiply those together. In the numerator, we have only 5. In the denominator, we have 2 times 2 times 2. So using your head or a calculator, that is 8. So simplifying 30 over 48 gives us 5 over 8. Those are equivalent fractions. They stand for the same thing. But 5 over 8 is written in lowest terms. Lowest terms means there are no more prime factors that the numerator and denominator have in common. Let's try the same thing with 22 over 45. So I'll make a factor tree with 22. 22 divided by 2 is 11, and 2 and 11 are both prime numbers. So 22 equals 2 times 11. 45 can be divided by 5. 45 divided by 5 is 9. 5 is a prime number. 9 can be divided by 3, and that is 3. We have all prime numbers, so 45 is 5 times 3 times 3. So we replace the original numbers with the prime factorizations. But even doing so will not give us any factors that are in common on top and bottom. And so really what we see from this is that 22 over 45 is already in lowest terms, in simplest terms. So we can go ahead and multiply the factors we have back together, and we get the original, 22 over 45. Sometimes we have fractions that are already in lowest terms, and that was definitely the case with 22 over 45. Let's try a few more examples. Now, on these next few, I'm not going to write the factor tree, but just know that is the way that you can find the prime factorizations of each of these numbers. And so if I were to write the prime factorization of 50, 50 is 2 times 25. 25 is 5 times 5. So the prime factorization is 2 times 5 times 5. 22 is 2 times 11. Now we see that the numerator and denominator have 2's in common. Cross out the 2's. Multiply the factors that remain. 5 times 5 is 25. We're left with just 11 in the denominator, so 25 over 11. And that is 50 over 22 written in simplest form. Let's go to the next number, 9 over 90. 9 can be rewritten as 3 times 3. 90 is the same as 2 times 45. 45 is 5 times 9. 9 is 3 times 3. So we have one set of 2's that are in common, one set of 3's that are in common, another set of 3's that are in common, and we see that all of the numerator cancels. That doesn't mean that we don't have a fraction any longer. That means that all of our factors are gone, and we're going to put a placeholder of 1. 1 over 2 times 5 is 10. So 9 over 90, written in simplest form, is 1 over 10. Now the last two problems we have on this page are special cases. When we divide by 0, which we see on the left, 24 divided by 0, or when we have 0 divided by a number, as we see on the right, 0 divided by 12. Think of this first example, 24 divided by 0, in the following way. If you had $24 and you wanted to divide that among 0 people, that would make no sense whatsoever. That would be impossible to do. We cannot divide by 0. So this does not exist. Another way we could say that, anytime we divide by 0, this fraction is undefined. Looking at the last example on this page, 0 divided by 12, let's think of a similar example, a similar situation to the one that we just thought of with 24 divided by 0. If I had $0 and I wanted to divide that to 12 people, it'd be pretty silly to try to do that, but basically I would give 12 people no money at all. And those 12 people might not be very happy, but it would be possible to do that. So 0 divided by any number that's not 0 will always have a solution, and that solution will be 0. It's important that we are able to distinguish between when the answer is 0 and when the answer is undefined. 0 on top is good. 0 in the denominator, 0 on bottom is not good. For the next few types of problems, we want to rewrite a fraction as an equivalent fraction with a larger denominator. Basically, it's the reverse of what we were doing when we were simplifying fractions. And this will be very useful when we try to add or subtract fractions that do not start with the same denominator. So let's look at the first example. We want to rewrite 4 over 9 as an equivalent fraction with a denominator of 27. What we have to decide is how we changed 9 into 27. Something must have happened to that 9 in order for it to become a 27 in its place. And what happened is we multiplied by some specific number. Well, we can go through our multiplication tables, we can use a calculator, but eventually we will determine that 9 times 3 equals 27. Using the fundamental principle of fractions, whatever we do to the denominator of a fraction must be done to the numerator of the fraction as well. So once we can pinpoint that number that 9 was multiplied by, in this case 9 times 3 equals 27, we will perform the same operation to the numerator. So because we multiplied by 3 in the denominator, we will also multiply by 3 in the numerator. 4 times 3 is 12. So if we rewrite 4 over 9 as an equivalent fraction with a denominator of 27, we end up with 12 over 27. A shortcut you can use if you're having trouble finding what number you should multiply by, take the denominator on the right and divide by the denominator on the left. And that will always give you the number that you should multiply top and bottom of your original fraction by. Let's try to use that trick on the second problem. Let's rewrite 6 over 7 as an equivalent fraction with a denominator of 27. And let's say that we could not find the number that we should multiply 7 by in order to get 28. So we're going to use our little shortcut. 28 divided by 7 equals 4. So we must have multiplied by 4 to get 28. Well, if we multiply by 4 in the denominator, we must also multiply by 4 in the numerator. 6 times 4 is 24. And now we have our equivalent fraction, 24 over 28. Now let's move on to multiplying and dividing fractions. In order to multiply fractions, we simply multiply the numerators together, straight across on top, and we multiply the denominators together, straight across on bottom. Dividing fractions is very similar with one extra step. We have to invert the divisor. Basically what this means is flip the second fraction. So that's the first step. We have to start by flipping the second fraction, and then we have a multiplication problem. So we flip the second fraction. Here you can see that C and D changed places. Then we multiply across the top, multiply across the bottom. Let's try a few examples of this. So let's multiply 2 over 7 times 3 over 5. Well, the first step isn't too bad at all. We multiply the numbers on top. 2 times 3 is 6. 7 times 5 is 35. We have to make sure that 6 and 35 don't have any factors in common. We have to make sure we simplify or rewrite this fraction in lowest terms. And so thinking about the prime factorizations of 6 and 35, 6 is 2 times 3. 35 is 7 times 5. The numerator shares no common factors with the denominator, so everything checks out. 6 over 35 is simplified, and that will be the product. Let's go to the next example. 1 over 11 times 1 over 3. Again, we multiply across the top. 1 times 1 is 1. 11 times 3 is 33. And here 1 can't be reduced any further, and it can't be broken down any further. So even if we rewrote the prime factorizations of the numerator and the denominator, 1 over 33 would be the simplest form. Once you have 1 on top or 1 on bottom, we can't break it down any further. And the last example on this page, 2 over 3 times 4 over 7. 2 times 4 is 8. 3 times 7 is 21. And just to double check, let's write the prime factorizations of 8 and 21 to make sure that there are not any common factors that might cancel. 8 is 2 times 4, and 4 is 2 times 2. So the prime factorization is 2 times 2 times 2. 21 is 3 times 7. And we can clearly see now that the numerator and denominator have no common factors. 8 over 21 checks out. It's in simplest form. And that would be the solution to that multiplication problem. Now let's try a few where we will need to simplify once we've multiplied. 3 over 4 times 8 over 11. So we multiply across the top. 3 times 8 is 24. 4 times 11 is 44. Let's rewrite the prime factorization for the numerator and the denominator. Remember, if you need to write a factor tree for the numerator, a factor tree for the denominator in order to find those prime factorizations, that is perfectly fine. Just for the sake of time, I'm going to write the prime factorizations for the numerator and denominator. So 24 is 2 times 12. 12 is 2 times 6, and 6 is 2 times 3. So we have that prime factorization. 44 is 2 times 22. 22 is 2 times 11. So now we have the prime factorization for 44. Now looking at the numerator and denominator, we have one set of 2's that cancels. We have another set of 2's that cancels. And those are the only common factors from the numerator and denominator. So we multiply the remaining factors. 2 times 3 is 6. We're left with only 11 in the denominator. So the simplified product, the simplified solution, is 6 over 11. Now let's look at an example where we have more than 2 fractions. We will actually work this the same exact way. All the numbers on top will be multiplied together. All the numbers on bottom will be multiplied together. So we take 2 times 3 times 14, and that gives us 84. In the denominator, we take 7 times 8 times 15, and that gives us 840. Now again, we may need to make a factor tree for each of these. I'm going to go ahead and write these prime factorizations out. 84 is 2 times 42. 42 is 2 times 21. And 21 is 3 times 7. 840 is 2 times 420. 420 is 2 times 210. 210 is 3 times 70. 70 is 7 times 10. And 10 is 2 times 5. So we just continue to break down each number until we have a product of only prime numbers. Now let's cancel the common factors. We have a set of 2's, another set of 2's, a set of 3's, a set of 7's, and that's it. Now because everything canceled in the numerator, we're going to put a placeholder of 1. In the denominator, let's multiply the remaining factors. 2 times 5 is 10. So the simplified result is 1 over 10. Let's try a few division problems, and we'll see these are very similar to the multiplication problems. 4 over 5 divided by 1 over 8. Remember, before we can divide, before we can actually work this problem, we write the first fraction exactly the same. We change the operation to multiplication, and we flip our second fraction. We invert our second fraction. So instead of 1 over 8, we write 8 over 1. Once we do so, now we multiply, just like we have before. 4 times 8 is 32. 5 times 1 is 5. We would try to write a prime factorization of the numerator and denominator. Once you try that, you'll see it checks out. There are no common factors, and 32 over 5 is the simplified quotient. Let's try another example. 14 over 17 divided by 2 over 5. Again, we write the first fraction exactly how we see it. Change the operation to multiplication. And we invert the second fraction. We flip it over. So instead of 2 over 5, we have 5 over 2. Now once we do that, we multiply. So we take 14 times 5. That's 70. 17 times 2. That's 34. And let's go ahead and write out the prime factorizations of each of these to see if we have any common factors. The prime factorization of 70 is 2 times 7 times 5. The prime factorization of 34 is 2 times 17. And we see that we do have common factors in the numerator and denominator, the 2's. So we cross out the 2's. Multiply the remaining factors. 7 times 5 is 35 over 17. Let's try a few more division problems. Now in part A, we haven't seen one like this yet. We have 3/5 divided by a whole number. Anytime at least one fraction is involved in the problem, we need to rewrite everything else as a fraction. And so let's do this. Anytime you have a whole number, we can make it a fraction by writing it over 1. Now we have 2 fractions. Let's work it just like the previous examples. The first fraction stays the same. Change the operation to multiplication. Flip our second fraction. Then we multiply across the top and across the bottom. Once we do so, remember to make those prime factorizations and cancel any common factors. So 3 is prime. It is its own prime factorization. The prime factorization for 45 is 3 times 3 times 5. I know I've said it a lot, but you can make a factor tree and find that rather quickly. We have 2 3's that are in common, so we cancel those 3's. Since the entire numerator canceled, we put a 1 as the placeholder. In the denominator, we have 3 times 5, which is 15. Let's try the next example, 3 over 12 divided by 1 over 7. Remember, when we divide, the first fraction doesn't change. The operation changes to multiplication. The second fraction flips. So instead of 1 over 7, we have 7 over 1. Now we multiply across the top and across the bottom. 3 times 7 is 21. 12 times 1 is 12. And just like any other multiplication or division problem, and as we'll see in a moment, addition and subtraction, we must try to simplify. So we make the prime factorizations. 21 is 3 times 7. 12 is 2 times 2 times 3. We have a 3 that cancels in the numerator and denominator. So we multiply the remaining factors, and that gives us 7 over 4. And we are finished with that division problem. Now for the last part of this section, we are going to add and subtract fractions. Before we can add and subtract any fractions, it is required that we have the same denominator. If for some reason we do not have 2 fractions with the same denominator, then we need to change, that's important, we have to change those fractions to equivalent forms until they do have the same denominator. Once we do that, we're going to combine the numerators, and the denominator will be the common denominator. The denominator will not add together. The denominator will not subtract. Once we have a common denominator, that will be the denominator for the result. So let's try a few examples where we start with the common denominator. If I have 3 over 8 plus 2 over 8, we have met the requirement of a common denominator. So we write that denominator one time, and we perform the operation with the numerators. Just like this, 3 plus 2. 3 plus 2 is 5, so we have 5 over 8. It's still important that we look at the numerator and denominator and make sure that nothing can be simplified, nothing can be taken out of each. So I'm going to write the prime factorization just to make sure. 5 is its own prime factorization. The prime factors of 8, 2 times 2 times 2. Nothing in common, so 5 over 8 is in simplest form. Let's try the same thing with 3 fractions on part B. Because each fraction has a common denominator, I can write it one time and perform the operations with the numerator. That gives us 3 plus 5 minus 4. Working from left to right, 3 plus 5 is 8. 8 minus 4 is 4. So we have 4 over 8. And again, it is important for us to try to simplify the fraction by writing the prime factorizations. The prime factorization of 4 is 2 times 2. The prime factorization of 8 is 2 times 2 times 2. We cancel common factors. Since all of the factors canceled in the numerator, we write 1 as the placeholder. We're left with a 2 in the denominator. So 1/2 is the simplified result. Now let's try a problem where we do not start with a common denominator. We need to find what is called the LCD. LCD stands for least common denominator. The LCD is the same thing as the least common multiple of the denominators. So we already know how to find the least common multiple. We did that in the last section. Let's go through those 2 steps. We want to find the least common multiple of 3 and 8. So we write the prime factorizations. 3 is a prime number, so 3 is its own prime factorization. 8, let's make a factor tree. 8 can be divided by 2 4 times. 4 is 2 times 2. So the prime factorization of 8 is 2 times 2 times 2. So when we look at each prime factorization, we see 2's and 3's. For the first prime factorization, we have 0 2's. For the second prime factorization, we have 3 2's. So the greatest number of 2's in any factorization is 3 2's. For our LCM, or in this case the LCD, we're going to include all 3 of those 2's. Now we're finished with the 2's. The most we ever see 3 show up in any given list. We see it once in the first list, 0 times in the second list. So the greatest number of 3's is 1. Finished with the 3's. And once we multiply these 4 numbers together, 2 times 2 times 2 times 3, that gives us 24. And 24 will be the least common denominator. Now once we have that number, we still have to do a little bit of work for each fraction in the original problem. Hopefully you'll remember seeing something similar to this just a few moments ago when we rewrote a fraction as an equivalent fraction with a new denominator. So for each of the original fractions, we want to rewrite those as equivalent fractions with a denominator of 24. So we can use our shortcut cheat method and divide 24 by 3 and determine that we need to multiply by 8 on top and bottom. And that will give us 16 over 24. In the second equation, 24 divided by 8 is 3, so we multiply by 3 on top and bottom. 1 times 3 is 3. We now have equivalent fractions with the same denominator. And the fact that they have the same denominator is important, and it is required. So we take these 2 new fractions, and we replace the 2 original fractions. 2/3 is equivalent to 16 over 24. So in the problem, we replace 2/3 with 16 over 24. We replace 1 over 8 with 3 over 24. And now that we have a problem with common denominators, we write that denominator one time, perform the operation with the numerators, and write the result. Now 19 is a prime number. We could try to write the prime factorization of the numerator and denominator. You would find that nothing simplifies. So 19 over 24 is the simplified solution. Let's try another. Let's try a subtraction problem. 10 over 11 minus 2 over 3. Again, we start by trying to find the LCD, the least common denominator. So we make a factor tree for 11. Well, 11 is prime, so it is its own prime factorization. Make a factor tree for 3, and again, 3 is prime, so it is its own prime factorization. So we have 11s and 3s in the prime factorizations. Each of those shows up once at most. And if you remember the trick from the first video, if each of your numbers are prime, we can just multiply those prime numbers together. So we multiply 11 times 3, the least common denominator is 33. Just like the last problem, we need to write equivalent fractions with a denominator of 33. So let's set up each of those equations and determine what to multiply numerator and denominator for each of these fractions in question. So we take 33 divided by 11 for the first fraction. We determine that we should multiply top and bottom by 3. 11 times 3 is 33. 10 times 3 is 30. So we have our first equivalent fraction. In the second fraction, 33 divided by 3 is 11. So we determine we should multiply top and bottom by 11. 3 times 11 is 33. 2 times 11 is 22. Just like in the previous example, we replace the original fractions with their equivalent counterpart. So in place of 10 over 11, we put 30 over 33. In place of 2 over 3, we put 22 over 33. Now that we have a common denominator, we write that one time. We subtract the numerators. 30 minus 22 is 8. Just like the previous example, we need to try the prime factorization. I'll go ahead and write it here. 8 is 2 times 2 times 2. 33 is 3 times 11. There just so happens that there are no common factors between the numerator and denominator, so 8 over 33 checks out. It is the simplified result. Now let's try a problem where we have a whole number minus a fraction. And you may see this come up from time to time. Just like when we tried to divide a fraction by a whole number, anytime we have at least one fraction in the problem, we need to rewrite everything as a fraction. So here we're going to write 6 over 1. Now we have 6 over 1 minus 1 over 7. We have two fractions that are being subtracted. We go through the same process we would before. We see that they do not have common denominators. So we need to start by finding the least common denominator, the LCD. So we make a factor tree to find the prime factorization of 1, and we find that 1 is its own prime factorization. 1 isn't really a prime number, but 1 always just equals 1. We do the same thing with 7. 7 is prime, so 7 represents its own prime factorization. And anytime we have two prime numbers, or if 1 is one of the numbers that we're dealing with, we multiply those two numbers together, and the LCD will equal 1 times 7, or 7. So we need to write each fraction as an equivalent fraction with the denominator of 7. So we write 6 over 1 equals something over 7. 1 over 7 equals something over 7. So for the first fraction, we take 7 divided by 1. That gives us 7. So we should see that we multiply both top and bottom by 7. 6 times 7 is 42. In the second fraction, we already started with the 7. And so nothing will change from the left side, the original fraction, to the new fraction. We already had the denominator we wanted. And sometimes that will happen. So we take the two equivalent fractions, the 42 over 7, 1 over 7, and put those into the original problem. So this becomes 42 over 7 minus 1 over 7. The answer will be over 7. 42 minus 1 is 41 over 7. 41 is a prime number. 7 is a prime number. Those are not going to break down. So the simplified result is 41 over 7. And that's how we add, subtract, multiply, divide fractions. Make sure to work hard and ask for help if you have any questions on these problems.